in a bit. I just got to do a couple things, like telling the entire group me that I'm doing this. Over the entire exam right now. All right, perfect. Hopefully some people pop in. If not, I guess that's fine.
Would want to have
And let me bring up my dashboard because that's kind of an important thing that you want to do in general. I feel like oh no, I'm fine. Okay. So video preview is closed. Okay, that's good. Let me just bring up this window, I guess. And this. All right, cool. So I guess I'm just going to go ahead and fuck, my phone popped out of my pocket. I'm gonna go ahead and go over the exam and I'll see what happens. I remember most of the questions. I just might be a little bit fuzzy on some of the numbers. So we'll just have to see how this goes. But I have a feeling it's going to go fine. All right, so let me get this out of the way. I think number 1 was not too bad if I'm not... Oh, yeah. Number 1 was easy peasy. So basically, you got a graph like this where here's your t, and then here's some variable epsilon. Right here is 1 over epsilon. This should be negative epsilon. This is positive epsilon. And you need to show that as epsilon approaches 0, f of t approaches the unit delta function, which is just like that function. The delta function is that function that spikes at 0 and then it integrates to 1. So this is pretty simple. So let's just take any arbitrary value of epsilon. We'll go and integrate from negative infinity to infinity f of t dt, which basically means we're actually just integrating from negative epsilon to 0. If you look here, the slope, this is just a line. The slope is rise over run, which is 1 over epsilon over negative epsilon, which is just negative 1 over epsilon squared. And my bad, it should be a positive epsilon here because you're moving up epsilon. So this is positive. And then the y-intercept is just 1 over e, or 1 over epsilon. So with that out of the way, we got 1 over epsilon squared t plus 1 over epsilon dt. Integrate this whole thing with respect to t. Infinitely tall, but still just 1. Yeah, I guess so. And then we also have this half, which is just the same, except it's negative. So it's the integral from 0 to positive epsilon of 1 over epsilon plus It should be minus 1 over epsilon squared t dt. And then you just evaluate this integral, we get t squared over epsilon squared plus t over epsilon evaluated from negative epsilon to 0. And then we add this to t over epsilon minus, there should be 2 here. I forgot how to integrate. It's t over epsilon minus t squared over 2 epsilon squared evaluated from 0 to positive epsilon. So once we plug in these values, at 0 it's just going to be 0, so we got 0 minus, and then at negative epsilon we have negative epsilon squared, which is just epsilon. That cancels out with, or that's squared, and then that cancels out with this epsilon squared, so it's just 1/2 plus, well, I'll just write this down, 1/2 plus, and then negative epsilon over epsilon is just -1, so here's that. We're going to add in this. Now at 0, this is 0. At epsilon, this is 1 minus 1/2. I guess I can include that if you guys prefer. And then pretty much all you have to do is sort of expand this out. So this is -1/2 plus 1 plus 1 minus 1/2, which equals 1. So as we can see, this function integrates to 1 regardless of what epsilon is. And the implication here is that integral from -infinity to infinity of f of t dt equals 1. However, if epsilon is approaching 0, then that means we have basically nothing, and then this this giant spike, and then this is basically the delta function. So this is essentially what we've shown. By showing that this integrates to 1, and that as epsilon approaches 0, the width of the integrable width sort of goes to 0, then we've shown that this is a delta function. That's kind of all I did for this exam question. I think I got at least most of the credit, if not all, because I'm pretty sure he did it during the review session. He did a problem just like this. So yeah, that was question number 1. That was worth 15 points, I believe. It was kind of an easy 15 points to pick up. All right, number 2 was you were given a circuit. Ooh, that was an odd sound. You were given a circuit with, I believe, an inductor, a capacitor, and a resistor. That's terrible. And then here is your Vn, your input function. Here's R, C, L. And then V out was the voltage across this resistor. And you're given I of T, which is the current, not the imaginary unit. Accidental ASMR. I guess so. So here was what we were given. Oh, actually, now that I'm thinking about it, there was no output voltage for this question. It was just this circuitry, and you were asked to find I of t using Laplace transformation. Not that hard, I would say, especially since you're given that there are no initial conditions, so there's no energy in any of these, either of these elements at t equals 0. So, oh yeah, I love that video where he just does like, I can't even do it on purpose, but I know the one you're talking about. It makes this great sound every time he does it. Classic moment. Anyway, let me make this a little bit. Oof. And then we're gonna basically just convert this. That was, I don't even know what I was going for. We're gonna convert this into the S domain by making everything its Laplace transform equivalent. Yeah, Laplace transforms, believe it or not, never come up in chess. So here we would have V input. Well, I guess this would just be V, right? Also, I'm pretty sure this was an actual value, which was 160 volts. This was 1 millihenry. This was... Okay, I don't remember what the resistance was. So actually, we're just going to use generic variable names for these purposes, because once you get, you know, the general form of the solution, you can just plug in the numbers as appropriate. So we got V over S here. Here you have LS, here you have 1 over CS, and here you have R. And then you have this I right here. And, oh god, my computer keeps falling asleep without my knowledge. I wish there was a way to disable screensaver. In fact, there probably is, to be honest. I should probably do that, but now's not the time. So we have this Laplacian current going through, and all we need is an expression for the current. So if we just use Kirchhoff's current law, we see that V over S equals I times the impedances of all these elements. So we got LS. Sounds like I'm missing a piece de résistance. Like, you mean with regards to my chalk? Just having friction against the chalkboard? Because yes. Oh yeah. That was a resistance joke. I see. Because I forgot the value of the resistor. That was good. I appreciate that one. Anyway, this is kind of what you get from Kirchhoff's voltage law. You know, you sum up all the voltage drops across the circuit, and then they had to add up to 0. This is an increase, not a drop, so we just sort of moved it to the other side of the equation. And then from here, we can do something magical, which is multiply everything by S, and we end up with V equals I LS squared plus 1 over C plus RS. And if we really want to make it, you know, pop, we're going to make this S squared plus R over L. Divide everything by, oh wait, this is not legal. Never mind. No, you can totally do this. Like V divided by L equals I times S squared plus R over L s plus 1 over LC. So you get this, and then you're trying to find the expression for I, so we just divide to get I to the other side, and then you end up with I equals V over L divided by S squared plus R over LS plus 1 over LC. Then you want to complete the square to sort of factor this, not sort of, actually factor this. So then we end up getting I equals V over L divided by, and then it is S squared plus R, that was the worst R ever, plus R over L plus R over 2L squared plus 1 over LC minus R over 2L squared. Reason I did this is because we just want to, we can see now that this is S plus R over 2L quantity squared, and then we end up on right here with, here, let me do some bracketing to show that these are equivalent. We got S plus, can you guys see that? S plus R over 2, yeah. We got just 1 over LC minus R over 2L squared. And then take the square root of this, multiply it by I, you get the whole idea. I actually think that this ended up being a positive number though, so you don't end up with any imaginaries. I could be wrong. But worst case scenario, you just end up with cosine of something or other. Hold up. Let me actually do the problem. So there's no square root here. This was just like the next step over. I hope you guys don't mind. We're going to sort of erase this stuff at the top. Doing it with actual numbers is so much easier, to be honest. So then S plus R over 2L squared plus 1 over LC minus R over 2L quantity squared. This is actually simply S plus R over 2L plus 1 over LC minus R over 2L squared I. And then you can guess what this part is. It's the complex conjugate. 1 over LC minus over 2L squared I. This should be a minus. And furthermore, nobody stopped me here. You gotta take the square root of this. Neat. So now that that's fully factored, you do the partial fraction expansion, and then you can convert it back into the time domain, and then you end up with like some constant cosine of alpha t plus beta, where beta is given by, if you do the partial fraction expansion, you get a complex number in the numerator. So it's b over a. So I'm explaining this poorly. If I had actual numbers, that would make things very convenient. However, I do not have the actual numbers, so this is what we're doing. I guess I'll just move on to number 3, since this is not going to be... This is sub-ideal without actual numbers. Hope you guys are satisfied with my board erase job. You'd do better in university if you did it all over. I mean, I think anyone could say that after they go through college. If they went back and did it again, they'd probably change some things about what they did and improve their experience. But hindsight is 20/20. We can't always, we can't look at our life in total hindsight. We have to consider what we were thinking in the moment to truly evaluate how well we did. Anyway, with that motivational speech out of the way, I'm trying to remember number 3. Number 2 is that number 3, I believe he gave us a fraction, and then we had to find the expansion of it. It was something like, in the denominator, I remember it was s to the 4th plus s squared. God, I don't remember at all what was in the numerator. It's crazy. I just took this exam, and yet I don't remember jack. Let me think. Because I have like a glimpse of it in my head. It was it was totally 10 minus s. If I'm not mistaken. Yeah, I think this was it. This is the problem. And then he said, do partial fraction decomposition to do the inverse Laplace transform on this D. PFD to ILT on this D. That was the question on the exam. And so we're just gonna go ahead and do it. So first things first, you gotta factor out this denominator. So it's 10 minus s. Here we can take out an s squared, and then we have s squared plus 1, which can be farther factored using, the principle of the hidden principle of a squared plus b squared equals a plus bi, a minus bi. We then get that it's s squared, s plus I, s minus I. So now that this is factored out, we can, first of all, we need to check, is the degree of the denominator greater than the degree of the numerator? And yes, it is. He kind of told us that we use partial fraction decomposition, so it spoils that part. But if that weren't the case, we could not do partial fraction decomposition. So good thing he didn't give us a broken question, I guess, is what I'm trying to say. This I can probably safely take off. You guys get it. So we can decompose this as follows. We have 10 minus s over s squared, s plus I, s minus I, equals a over s plus b over s squared. You guys can see that, yeah. Plus c over s minus I plus d over s plus I. And then what we do is we're going to multiply everything by this denominator. So we got s squared, s plus I, s minus I. And then this will give us 10 minus s equals a s minus I, s plus I, plus b s minus I, s plus I, plus c s squared, s plus I, plus d s squared, s minus I. Now that we have this, we can choose any value for s, and these coefficients all have to still make sense. So what we're doing is we're basically saying, all right, let's just, for example, let s equals 0. This term goes away, this term goes away, this term goes away, because, you know, the s is 0 and 0 times anything is 0, so it multiplies out to 0. So then you're left with 10 minus 0 equal, oh, you know what error I'm making here? I think it was actually s minus 10 this entire time. So then we get 0 minus 10 here. This goes away. We got b minus I plus or times positive I. No, my laptop fell asleep again. It's so tired. All right, let me actually fix this while I still have the opportunity. So we're gonna go to settings. Detail power. This is probably it. All right, cool. I just changed my settings, so it shouldn't go to screensaver anymore. So we have negative 10 equals b times negative I times positive I. I times I is negative 1. We negate that, so it's 1. So we get negative 10 equals b. Cool. Next step, we'll take s equals I. I minus I is 0. This goes away. This goes away. This does not go away. This goes away. So we have negative 10 plus I. I know it's I minus 10, but I like the imaginary unit at the second part. Just a preference of mine. Equals C times S squared. Well, S is I, so it's just negative 1. And then we have I plus I, that's 2I. So then all we have to do is divide by negative 2I, which is what this multiplies out to. But we have to multiply this other side by 2I, or negative 2I, divide it And then we get that c equals -1/2 minus 5i. If you need me to walk you through how I did that, all I did was I took -10 plus I over -2i, multiplied both the numerator and the denominator by 2i. This gives us, multiplied by I, not 2i. So this gives us -10i minus 1 over 2, which then leads to this homeboy right here. Cool. All right, now that that's settled, we get c equals -1/2 minus 5i. That means that d equals -1/2 plus 5i. And we're going to leave this as an exercise to you guys to prove why this is true. But essentially c and d have to be complex conjugates because their denominators are complex conjugates, and there are no other complex denominators in the expansion. So I hope you'll just take my word for it. It is true, and it's provable, but I'm not going to go through the effort. So now we have B, C, and D, which is good. But how do we get A? Because problem is, there are no factors that this has that none of these other ones have. So we can't just eliminate them like we did before. However, what we can do is just choose any old value of S. One easy one to work with, perhaps, is S equals 1. And you'll see why that's the case in a second. So we got 1 minus 10 equals A, 1, 1 minus I, 1 plus I, plus B, which is -10, 1 minus I times 1 plus I, plus C, which is -1/2 minus 5i. S squared is just 1, and then we get 1 plus I, plus D, which is -1/2 plus 5i. And then you multiply that by S minus I, which is 1 minus I. Alright, cool. So we get -9 equals 1 minus I times 1 plus I. What is this? Well, it's 1 squared minus I plus I minus I squared. I squared is -1, so it's really plus 1. These two i's cancel out, and then you're left with 2. So we got 2a. Here we got -10 times, this is still 2, so plus, and then what do we have here? We have, we'll just write it out, -1/2 minus 5i minus 1/2 I. It should be minus 5i squared, but that's plus 5. And then for D, you get -1/2. We get plus 5i plus 1/2 I, 5i times I, that's negative 5i squared, that's 5. Notice how these cancel out. Hold on, something ain't right here, I believe. Could be wrong though. Let's see. You have 1/2 plus negative 1/2. That's the same in both cases. Yeah. 1 plus I, 1 minus I. Okay. False alarm. I thought something was wrong, but nothing was wrong. So we got negative 9 equals 2a minus 20 plus, and then we have 5 is 10 halves minus 1/2, that's 9 halves, but we have 2 of them, so we get plus 9. And then we get, from adding, this is negative 11, so we're going to add that to the negative 9, we get negative 20 equals 2a, and we get that a equals negative 10, which is admittedly not what I got on the exam. I got negative 1. So that kind of blows. However, it's fine. We'll just keep going. We move along. We move on. We truck along. We keep going forward. So once you expand this out, which is pretty simple, we can just sort of replace these letters with what we have. So we got negative 10 here. B is also negative 10. 1/2 plus 5. That's 9 halves. Yeah, that's correct. Okay. C is negative 1/2 minus 5i, and D is negative 1/2 plus 5. Alright, so now that we have this, enjoy this brief intermission as I erase the board. Hope you guys are having a good time. I'm having a real good time. Okay, cool. So here's our expression for f of s, and then all we have to do is do the inverse Laplace transform on this whole business. This should not be a parenthesis, this should be a curly brace, because we like curly braces here. Alright? Good. So then we get, well, we're going to convert this into t, so it's just negative 10 u of t. That's the unit step function. If you know your Laplace transforms, you get this. And then this is negative 10t. Now, these two, if we look closely at our table of transforms, we get, we see that this is the negative one, which means that this is what we take the arctangent of to get our phase angle. So, it ends up being the magnitude of this, which is square root of 5 squared plus 1/2 squared, which is square root of 25 plus a fourth, and that is square root of 101/4. Square root of 101 over 2, if you prefer that. So we get 2 times that, which means square root of 101. And then the cosine, our alpha is, or I'm sorry, it should be our beta. Our beta is the coefficient of the imaginary in our denominator, which is 1. So we get just t, 1 times t. And then we have to add the phase angle, which is, as we discussed earlier, the arctangent of 5 divided by 1/2 is the same thing as 10. So we got arctangent of 10 here. And ladies and gentlemen, I don't feel like getting out my calculator. This is our final answer for number 3. And this is exactly what I got on the exam, except for this part. This was a 1. I don't understand how I got 1 instead of 10, but whatever. I got this part correct, which is the most important part. So there we go, ladies and gentlemen. This was the problem at hand. So let's go on to number 4, which I believe was the convolution problem. So this problem I definitely messed up on, which sucks, but it's okay. Sometimes you gotta just let the deal go down and ride that mystery train. Oy vey. Alright, sick. We finish up here. My eraser ain't looking too hot, so let me get another napkin. I don't own an actual chalkboard eraser. In fact, this chalk is being borrowed from a friend, so I don't have any actual chalk either, and it doesn't come with the board. So that's a shame. So I'm just making do with what I have. Anyway, number 4 looked a bit like this. We had this t-axis going from 0 to 3, and then the this was 1, and this was our x of t. And then we also had something similar over here, where it went from 0 to 1. And then the function value was 2. And this was our h of t. So all we needed to do was use semi-graphical convolution to find x of t convolution with h of t. Now, mathematically, this is equivalent to the integral from negative infinity to infinity of x of t minus lambda h of lambda d lambda. However, what are these functions? Well, if you look at x of t, you know that it's unit step function minus, or at 0 unit step function minus unit step function at 3. So in other words, this is u of t minus u of t minus 3. Which means that x of t minus lambda is u of t minus lambda minus u of t minus lambda minus 3. I don't know if this I don't know if this means anything to you guys yet, but trust me, it's gonna make sense. So what is this h of t? Well, this h of t is just kind of 2, because the peak is 2, and then it's u of t minus u of u of t minus u of t minus 1. So since t is just a dummy variable, we can replace it with this lambda. So we got h of t minus t plus lambda. No, h of lambda equals 2 u of lambda minus u of lambda minus 1. Alright, cool. We have our x, we have our h. What does that mean? That means that, well, first of all, we know that y of t is this convolution, because that's what we were told. It also makes sense if you consider what the transfer function actually is, but you don't even have to do that much. And then, what was I saying? Oh. So basically what the convolution is doing is, let's just say you layered the graphs on top of each other with respect to delta. Here's our x of t. Here is our h. And then this intersection is what we're finding the area of in the convolution. By the way, thank you to Nicholas for explaining to me what the deal with this problem was. I completely missed the mark on the exam when I did this. But it's actually really simple. So notice, if this is our range from 0 to 1 for t, how should I explain this? This is t, not lambda. Well, no, actually, it is lambda. Here we have t equals 0. Or I'm sorry, lambda equals 0. God damn. I'm getting these variables mixed up. Here we have t, and here we have t minus 1. How we got that was we kind of just flipped this over such that it's instead of being t, this axis is now negative. well, I guess it would be negative lambda. So since this was positive lambda, this is what this looks like. And then we have, oh, you know what? I kind of have it backwards. So there are two forms of the convolution. They both have the same value. However, what we really want is this for this graph I just drew to make sense. So we're essentially going from lambda equals 0 up to t at this point. And then when we're sort of, as you increase delta, this sort of shifts, or as you increase t, excuse me, this one sort of shifts this big bar over. So this is from -1 less than or equal to t less than or equal to, well, actually, we don't use negative time when we're doing this. So t goes from 0 to wherever t minus 1 is 0, so that's just 1. And then we get, by the way, this is 3. So we get 3, and then whoosh, whoosh, whoosh. Here's our integral. Here's our t minus 1. Here's our t. And then here's lambda 0. So here we're going from lambda equals t minus 1 to t. And then lastly, we have this whole ordeal, which is, man, my 3 is getting skinnier and skinnier, closer and closer to the origin. All these op-amps, that's just the background. It doesn't mean anything. The question was the convolution one on the exam. I don't know if you could have the same numbers, but it was, we had this excitation graph for x of t, this one for h of t, and we had to find y of t equals the convolution of x of t and h of t. So I'm a fool. Yes, lambda goes from t minus 1 to t here, but the range of t's for which this is the case is t goes from 1 to 3. And then now we have this last case, which is t goes from 3 to 4. And we're finding this is a t minus 1, this is 3. So lambda goes from here. Let me mark down where lambda goes. 0 to t in this case. You got t minus 1 to t. And here we have t minus 1 to 3. It will be a trapezoid. Yes, it will. But that's the resultant function. The resultant function is going to be a trapezoid. This is just graphically demonstrating what the convolution is. So let me erase something. I guess this stuff I was working on earlier that turns out isn't actually what we want. So for any given t, in this range, from 0 to 1, we get y of t equals integral from 0 to t of, now the thing is, if you multiply at any given lambda the value of this times this, in all the intervals we're talking about, we're going to get 2. So it's just 2 d lambda. And then that results in 2 lambda evaluated from 0 to t. So we'll do lambda equals. And then that's just 2t. So here's our function for this interval. For this interval from 1 to 3, we have y of t equals, and then it's integral from t minus 1 to t of 2 d lambda, which is just 2 lambda from t minus 1 to t, which is 2t minus 2t minus 2, which, this becomes a plus, so it's just 2. And then lastly, we have this interval, so it's from 3 less than t to 4, we get y of t equals integral from from t minus 1 to 3 of 2 d lambda, which is 2 lambda evaluated at t minus 1 and 3. That's 2 times 3, which is 6, minus 2t plus 2. So that's 8 minus 2t. So now that we have these intervals in place, convolution is kind of trash, yeah. So now this would be an acceptable answer on the exam, but just for demonstrative purposes, I'm going to show what the actual graph of this looks like, as one would expect. It's a trapezoid. So we have, here's our t-axis. Here is our y of t. I was trying to think of what letter the function was. It's y. Our significant values are 0, 1, 3, and 4. And then we have 2 right here. So it's 2t. You can see that the slope of this line is 2. All the way up to 1, and then at 1 it flatlines at 2 until we get to t's between 3 and 4, in which case it goes down all the way to, at 4 it's 0. So bam, we can see that the slope of this line is -2, which is as expected. And from t equals 4 onward, it is just 0. So yeah, this is our graph. This was the convolution, and we are moving on because I hated that problem. All right, that was number 4. Let me think. What was number 5? It was, you were given, all right, this was the easiest one on the whole exam. There are no excuses for having done poorly on this. There was a sinusoidal Vn, which it told you was a sine wave. There was some value of L. I don't even want to put in actual values. That's gross. Here was our plus minus Here's our R. Here's a capacitor, and here is an inductor. So now, it was asking for A, or I'm sorry, it was the center frequency. For part B, it was asking for the quality, and part C, it was asking for the bandwidth. So what's funny about this is if you have on your equation sheet written down, what kind of question is that? To calculate a convolution doesn't examine your knowledge of the material whatsoever. Well, I mean, I guess there are some cases, like if you're actually engineering a circuit where you'd want to do a convolution. I can't think of any such situations, but maybe hypothetically one would exist. But it is material in the book that he went over in lecture, so that's why it was on the exam. It was worth 25 points though. That one question was worth 25 points, which is ridiculous. Anyway, here we have the center frequency, which if you were clever and wrote it down on your equation sheet, which I think most of the students taking the exam probably did, this is just, first of all, angular frequency divided by 2 pi, which is 1 over square root of LC over 2 pi. And then this was your answer. Yeah, this problem was really just free points. Now this bandwidth, funny thing about this bandwidth is that you needed to calculate part B. Part B comes first, so whatever. Point being, the bandwidth is R over L. That's your answer. And then the, oh wait, my bad. The bandwidth is R over L. However, this is in radians per second, so you have to convert it to hertz. So it's actually R over L times 1 over 2 pi hertz. And then that, this is your answer. And then part B was the quality. Now there is a formula that's like square root of R squared C over L, something like that. I didn't do that. I did the much simpler omega naught over bandwidth, where the bandwidth is in radians per second. So then you end up getting, oh, I guess the same thing I wrote down. It would be 1 over square root of LC times L over R, which is square root of L over R squared C. So this would be your answer for the quality. What course was it? It was Principles of Electrical Engineering 2. Basically, in Principles 1, we went over mostly resistors, and then we did a frequency domain analysis to treat inductors and capacitors as impedances. But we didn't go over how inductors and capacitors actually worked that much in depth. Here, it's basically inductors and capacitors and how they work and how we can use Laplace transforms to sort of skirt around needing differential equations to figure out their behavior. Alright, so that question was an easy 15 points. If you got any of those wrong, that just amounted to you not utilizing your one sheet of equation well. By the way, if you're not in this class, the professor allowed us one side of a sheet of paper to write down any equations that we wanted to use for reference. Now, you could hypothetically derive the center frequency and bandwidth and quality from scratch using the circuit. However, that is a chump move because you would have run out of time because, you know, it takes forever. Where do we study? I study at Rutgers University. If you look, wait, hold up. Right here, there's a Scarlet Knight, and that is the mascot of our school. The electrical engineering program, kind of alright-ish here. There are some questionable parts, but also it's a lot better than people say. It's underrated, I would say. All right, let's go to question number 6. Question number 6. It gave you f of s equals, I remember the numbers for this one very distinctly, s squared plus 7s? Yeah, plus 14. S squared plus 3s plus 2. And then it told you to use partial fraction expansion on it. Or, no, my bad. It was find the inverse Laplace transform of f of s, which involves using partial fraction expansion, essentially. Now, just looking at this right now, I made an error on the exam. The degree here is the same as the degree here, and the partial fraction expansion doesn't really work if that's the case. So what we actually need to do is we need to divide this polynomial by this polynomial and see what we get. S squared plus 3s plus 2. Alright, so this goes in once, and then we get s squared plus 3s plus 2. We subtract here, and we end up with 4s, I can't math today, plus 12. And then that's our remainder, so it's 4s plus 12 over s squared plus 3s plus 2. Now, we have, this is the same expression as f of s. We didn't modify it in any way, so we can say f of s equals 1 plus 4s plus 12. That was the worst plus sign of all time. We got s squared plus 3s plus 2. And now this is what we want to use partial fraction expansion on. So that's 1 plus 4s plus... We're going to factor this, actually. Never mind. I thought factoring was going to give us something cool, but it didn't. So we're just going to leave it in this form. So now we have 4s plus 12 over s plus 2 times s plus 1. And then that equals a, worst a of all time, a over s plus 2 plus b over s plus 1. As we've done for the previous problems, we multiply this whole thing by s plus 2 times s plus 1 to get 4s plus 12 equals a times s plus 1 plus b times s plus 2. And then we consider s equals -1. Then we get -4 plus 12 equals b. -1 plus 2 is 1. So we got b equals 8. Cool. And then we consider s equals -2. We get -8 plus 12 equals, that goes away, -2 plus 1 is -1, -a. So we get a equals -4 out of that. So then we get that f of s equals 1 plus, or, well, I guess I'll do minus 4 over s plus 2, and then plus 8 over s plus 1. A will be 8, B will be... Oh, you, I guess I should write a little bigger, because my webcam isn't highest quality. So, but yeah. Equals 8, A equals -4. And believe it or not, this is kind of what I got, even though I made the mistake of not doing this step. But basically, we want the inverse Laplace transform of 1 minus 4 over s plus 2 plus 8 over s plus 1, which happens to be the delta function, interestingly enough. Minus 4e to the negative 2t plus 8e to the negative t. And ladies and gentlemen, this is our final answer. Wait, let's not forget the u of t here. That's kind of an important detail that I think I missed, to be honest. All right, cool. So that was number 6 of the exam. When the denominator poles are first order, there's a simpler way. Oh yeah, I would sure believe so. It has something. I see the ratio here, like, it's a 2-to-1 ratio, and then these addends are a 2-to-1 ratio, so probably has something to do with that, if I would guess. But I'm looking forward to learning an easier way to do this. However, that was number 6 of the exam, and that then closes out all the questions, so we're basically done here. If there's anything else that you... Well, I mean, since none of the people in the class are in the chat right now, I'm not really going to take recommendations from complete strangers about problems to do. Unless you really want me to. Like, do you have any problems that you want me to, like, do as a demonstration? Because if not, then I think I'm going to close out the stream for now. I'll be back on later tonight playing a game. Whence is 4s plus 12 divided by s plus 2, s plus 1. You could place s equal -2 and just ignore the s plus 2 part. Yeah, that's a shortcut. Oh, I see. Okay. You just ignore the factor of 0, basically. That makes sense. It's not like you're doing anything invalid, it's just kind of shortcutting to the correct answer. I see. That's pretty good. That's pretty clever. But of course, the graders for this exam would take points off if I didn't show all my work, so I didn't want to risk anything anyway. More poles, but only of first order. Yeah, that makes sense. I think I've heard about that method once. I think I saw it in a video of some sort. Anyway, thank you for participating in the chat. I'm gonna get going soon. Or right now, pretty much. I'll be back on later doing something unrelated to this. Probably something a little bit more fun. And hope you enjoy the rest of your evening. Take care.